3, 2, 1. Hi guys, it's the Microwave Bros here, and today we'll be discussing the microscope. So what is a microscope? Is it a weapon? Is it a tool? No, it's an instrument.
Like a guitar?
No, it's not an actual instrument, but it's an instrument used in the laboratory to observe small objects that can't be seen through the naked eye. Pretty cool, right? By the end of this video, you should be able to identify the parts of a typical microscope and learn their functions. Focus specimens under the compound microscope and dissecting microscope. And lastly, measure specimens under the microscope. Now, let's learn more about the microscope. Let's call in Jana and Den to talk about it.
Hello, we'll be introducing the parts of the microscope and its functions. We'll be starting from top to bottom. First, the eyepiece, which is also called the ocular. This is the part of the microscope that magnifies the image produced by the objective lens by 10 times. It basically magnifies the magnified image. The eyepiece also consists of a pointer that indicates what part is being viewed. Moving on, connected to the end of the eyepiece is the revolving nosepiece. This consists of 4 objective lenses, 4 times, 10 times, 40 times, and 100 times. Let's go more in depth with this. Again, there are 4 objective lenses, namely the scanning lens, LPO or low power objective, HPO or high power objective, and OIO or oil immersion objective. These are used to further enhance the magnifications of the viewed specimen. To view a specimen, it is placed on a stage, a flat platform designed to support the slides. This is also where the stage clips are located, to hold the slides in place. But what should we do if the image is not clear?
Don't worry, there's a way to resolve this problem. One must use the substage condenser. It is responsible for gathering light from the light source, which later will be forming a cone of light in order to get a clearer image of the specimen. There are 2 possible light sources, the mirror and substage illuminator. In order to adjust the intensity of light, you can use the iris diaphragm. The iris diaphragm is used to control the amount of light that reaches the specimen. Is there a way to adjust the light output? Yes, through the use of the illuminator control knob, the light output can be controlled. You might be wondering, what is the purpose of the other 2 knobs? First, the coarse adjustment knob. It allows for quick focusing by moving the objective lens or stage up and down. On the other hand, the fine adjustment knob focuses sharply on the specimen using low power.
Now that we know the parts of the microscope, let's talk about its magnification. Again, there are 4 objective lenses, namely scanner, LPO, HPO, and OIO. Each differs in magnification, as you can see, although we may think that this is the total magnification capability of these lenses. Well, it actually isn't. We must also take into account the magnification of the eyepiece, which is 10 times. So, in order to get the total magnification, you must multiply the magnification of the eyepiece by the magnification of your objective lens. Let's go back to the 4 objective lenses. But now, let's apply the formula. We've got the total magnification of each lens, which is 40 times, 100 times, 400 times, and 1000 times.
Have you ever noticed that even though you've adjusted the coarse and fine adjustment knob, the specimen still appears blurry? This may be due to the lens quality. The quality of lens can greatly affect the visibility of the image. Even if given a high magnification, but is low in resolution, the image will not clear up no matter what.
The resolving power denotes the smallest details that a microscope can resolve when imaging a specimen, enabling you to look at its finer details. Take note that the resolution can also be affected by the cleanliness of the lens. Make sure that it is always clean before and after every use.
Have you ever wondered why objects or specimens viewed through the microscope are inverted? According to Ward, the reason this happens is that the microscopes use two lenses to help magnify the image. Another consequence of this is the light. You see the light source beneath the slide of the specimen. Once it comes out from under the slide, two rays converge to make an enlarged and inverted image.
Moving on, let us talk about the field of view. In the field of view, we have something called parfocal. It refers to objectives that can be changed with minimal or no refocusing. This means that even if you are switching objectives, one is just magnifying the specimen more but with a slight movement of the adjustment knobs. Remember, it is important to center the specimen before increasing the magnification in order for them to stay in sight.
Did you know that there is a tiny ruler within the microscope? It's actually called the ocular micrometer. It is a tiny circular glass or plastic etched with a non-unit scale that ranges from 0 to 100. There is also another miniature ruler, but it's now found on the glass slide, which is called the stage micrometer. It has a scale of known units that are divided into 0.02 millimeters graduations. Now we are given the task to compute for the calibration constant of LPO and HPO. Here's how the specimens appear under the microscope. Let's look at the specimen under the high power objective. If you look closely, there are two rulers present, the ocular micrometer and stage micrometer. Whenever computing for the calibration, take note that the zero line of the ocular disc scale must be aligned with that of the stage micrometer scale.
Now let's locate the first point where the two lines exactly align with each other. Here, the distance from 0 on the stage micrometer is 25 millimeters, while there are 100 ocular divisions on the ocular micrometer. After getting these values, follow this formula. 1 ocular space slash calibration constant equals stage micrometer spaces over ocular micrometer spaces times 0.01 millimeters. Afterwards, to express the calibration constant in micrometers, simply multiply the ocular space in millimeters by 1000. Now let's put in the values for both LPO and HPO into the formulas, which now result to a calibration constant of 10 micrometers under LPO, while 2.5 micrometers under HPO. What did you notice from the results? We noticed the increase of magnification upon the results. The next task is to determine the width of the paramecium under LPO and HPO. Here's how the specimen appears under the microscope. To solve for the width of the paramecium, simply multiply the measurement of the specimen to calibration constant we've previously answered. What did you notice from the results? Through multiplying the measurement of the specimen, the calibration constant is merely more than twice its width.
Now that we've understood the functions of a compound microscope, did you also know that there's another type of microscope called the dissecting microscope? What makes them different from each other is that the dissecting microscope are used to view the surface features of a specimen, whereas compound microscopes are designed to look through a specimen.
Hi guys, that ends our video for today. You're now a master on how to use the microscope. We hope you enjoyed and learned something in our discussion. Peace, we out!